The most important artificial intelligence race is not happening inside a chatbot. It is happening in chip factories, power stations, data centers, research labs, and corporate balance sheets. In 2025 alone, global corporate investment connected to artificial intelligence reached almost $582 billion. By 2026, individual technology companies were planning infrastructure budgets once associated with national megaprojects. Amazon said it expected roughly $200 billion in capital spending during 2026. Alphabet projected between $175 and $185 billion. Meta raised its expected range to between $125 and $145 billion. OpenAI and its partners described Stargate as a $500 billion infrastructure program. These numbers are not the price of better chat windows. They are the cost of building a new industrial system for intelligence. And the real question is no longer simply who has the smartest model. It is this: who can secure the chips, electricity, capital, talent, and customers required to make intelligence available at global scale? For decades, artificial intelligence advanced in waves. New ideas appeared, demonstrations impressed researchers, and excitement faded when the technology could not scale. Then, several systems began reinforcing one another. In 2012, a deep neural network called AlexNet showed how graphics processors could train machines to recognize images with a dramatic improvement over earlier methods. In 2017, researchers introduced the transformer. Its attention-based design allowed models to process information in parallel, making it practical to train much larger systems. In 2020, GPT-3 demonstrated that scale itself could unlock new behavior. A single model could write, translate, answer questions, and adapt to tasks from instructions and examples. Then, in November 2022, ChatGPT placed that capability in front of the public. The breakthrough was not only technical, it changed expectations. Within a few years, generative AI reached an estimated 53% population-level adoption worldwide. Organizations began embedding it into software development, customer support, search, advertising, education, medicine, and scientific research. Artificial intelligence stopped looking like a research category. It began looking like a general-purpose technology. But every useful answer, generated image, or automated task required something hidden: enormous computation. And once demand became global, computation became the scarce resource everyone wanted to control. Modern AI begins with an algorithm, but it runs on silicon. Training a frontier model requires thousands of specialized accelerators connected by high-speed networks. Serving that model to millions of people requires even more machines working continuously. This made NVIDIA one of the clearest financial winners of the AI boom. In its 2026 fiscal year, the company reported nearly $216 billion in revenue, with data center revenue rising sharply as customers raced to deploy its systems. But NVIDIA does not manufacture its most advanced chips alone. That work depends heavily on TSMC, the Taiwanese foundry capable of producing leading-edge processors at extraordinary precision. It also depends on advanced packaging, high-bandwidth memory, networking equipment, cooling systems, and a global chain of chemical and equipment suppliers. A single AI accelerator is therefore not one product. It is the final result of an international industrial network. This is why the AI race quickly became geopolitical. The United States tightened controls on the export of advanced computing chips and semiconductor technology. China accelerated efforts to build domestic alternatives. Governments offered subsidies, negotiated supply agreements, and treated data centers and chip factories as strategic infrastructure. At the same time, the largest cloud companies began designing their own processors. Google developed TPUs. Amazon expanded Trainium. Microsoft and Meta pursued custom silicon. The objective was not necessarily to replace NVIDIA everywhere. It was to reduce dependence, lower costs, and gain control over the most important input in the system. Hardware alone is not enough. NVIDIA's position also rests on years of software, developer tools, networking, and optimized libraries. A cheaper processor can still lose if customers must rewrite their systems or cannot run workloads reliably. The chip race is therefore also an ecosystem race. Performance matters, but compatibility, availability, and the speed of deployment matter with it. The first layer of the AI race, then, is not the model. It is access to the machines that make the model possible. A warehouse full of chips is still not an AI system. The chips must be assembled into data centers with power, networking, cooling, security, and enough land to expand. They must be connected to software that can divide enormous workloads across thousands of machines without wasting time or energy. This is where the race becomes physical. Amazon explained that cloud infrastructure must be financed months before customers can use it. Land is acquired, power is reserved, buildings are constructed, chips and networking equipment are installed. Only then can the capacity begin producing revenue. The scale is difficult to visualize. OpenAI said its Stargate initiative was designed around 10 gigawatts of planned capacity. 10 gigawatts is not merely a large computing project. It is power demand on the scale of major cities and industrial regions. The International Energy Agency projects that global electricity consumption by data centers could roughly double from 2025 to 2030, reaching about 950 terawatt-hours. AI-focused facilities are expected to grow much faster than conventional data centers. Power is not interchangeable. A data center needs electricity at a specific location, at a reliable price, and on a schedule that matches construction. New generation may be available nationally, while the local transmission network remains congested. That is why technology companies are signing long-term power agreements, considering nuclear energy, and searching for regions where land, permits, fiber, and electricity can be secured together. That changes the meaning of competitive advantage. A company may have brilliant researchers and a powerful model, yet still be unable to expand because a grid connection takes years. A region may attract billions in investment, yet face pressure on water, electricity prices, construction capacity, and local infrastructure. The bottleneck may no longer be code. It may be a transformer at an electrical substation, a shipment of high-bandwidth memory, a cooling system, or permission to build another transmission line. Artificial intelligence has become software with the supply chain of heavy industry. The companies at the frontier are spending at unprecedented speed because the technical lead is fragile. Stanford's 2026 AI Index found that the performance gap among top models was narrowing. It also found that the distance between leading American and Chinese systems had nearly disappeared on several major evaluations. That does not mean every model is equal. Reliability, safety, reasoning, coding, multimodal capability, speed, and cost still vary. But it does mean that a breakthrough may provide only a temporary advantage. Competitors can study published research, hire experienced teams, improve training methods, and build on open-weight models. Smaller systems can sometimes match older frontier performance at a fraction of the cost. Better software can make existing hardware more efficient, so the race has two opposing forces. One force pushes toward scale: larger clusters, more data, longer training runs, and more expensive infrastructure. The other pushes toward efficiency: smaller models, specialized chips, better algorithms, compression, and cheaper inference. This tension explains why the largest companies are not betting on one model. They are building platforms. Microsoft connects models to Azure, Office, Windows, and developer tools. Google links them to Search, Android, YouTube, Cloud, and its advertising system. Amazon combines cloud infrastructure, custom chips, commerce, and enterprise distribution. Meta can place AI inside products used by billions of people. The advantage is not only intelligence, it is the ability to distribute intelligence, collect feedback, finance the next generation, and reduce the cost of every interaction. There is a problem beneath the excitement. Building frontier AI is expensive. Operating it is expensive, and many users expect the service to be free. The industry is therefore searching for business models large enough to justify the infrastructure. Some companies sell subscriptions. Others sell access through application programming interfaces. Cloud providers rent computing capacity. Software companies use AI to protect existing products or charge more for premium features. Advertising companies hope better recommendations and automated creation will increase revenue. The opportunity is real. Stanford estimated that the annual value American consumers received from generative AI had reached $172 billion by early 2026. Adoption inside organizations also continued to rise, but value to users is not the same as profit for providers. The infrastructure must be purchased before demand is fully known. Chips can become outdated quickly. Competitors may lower prices. Open models can reduce the ability to charge a premium. New techniques may suddenly make yesterday's expensive capacity less valuable. This creates the central financial risk of the race: overbuilding. The same infrastructure can also create a price war. When several companies build capacity at once, each has an incentive to keep expensive machines busy. Lower prices can attract more usage, but they can also compress margins before the investment has been recovered. Efficiency improvements make AI cheaper to use, yet they may reduce the revenue earned from each task. Growth can accelerate while the economics remain unsettled. If demand continues to expand, today's data centers could become the foundation of a new economy. If revenue grows more slowly than infrastructure, companies could be left with enormous depreciation, debt, and power commitments. History offers both possibilities. Railways, telecommunications networks, and the early internet were often overbuilt. Investors lost money. Yet the infrastructure still transformed society because later users benefited from capacity that already existed. The AI race may follow the same pattern. The companies that finance the system may not capture all of its value. But once the system exists, entire industries can be rebuilt on top of it. The competition is often described as a contest between companies. It is increasingly a contest between national systems. The United States leads in private investment, frontier laboratories, cloud platforms, and many advanced chip designs. Taiwan remains central to leading-edge manufacturing. The Netherlands and Japan supply critical semiconductor equipment and materials. China combines research scale, industrial capacity, a vast domestic market, and a determined effort to reduce foreign dependence. Gulf states are using capital and energy to position themselves as new computing hubs. No country controls every layer. This is why the language of technological sovereignty can be misleading. Countries can strengthen domestic capacity, but complete independence would require duplicating decades of specialized knowledge across design software, lithography, materials, memory, packaging, construction, and energy. The more realistic objective is resilience. Enough trusted alternatives and partnerships that one disruption does not stop the entire chain. That interdependence creates both strength and vulnerability. A disruption in Taiwan could affect the supply of advanced processors. Export controls can slow access to certain chips, but also encourage substitutes. Energy shortages can delay data centers. Immigration rules can influence where researchers choose to work. Regulation can shape which systems can be deployed and who is responsible when they fail. The race is therefore not won by a single invention. It is won by coordination. Research must connect to manufacturing. Manufacturing must connect to energy. Energy must connect to data centers. Data centers must connect to products. Products must create revenue. Revenue must finance the next round of research. A weakness in any layer can limit the entire system. That is the hidden structure behind the headlines. So, who is winning the artificial intelligence race? The honest answer is that the finish line keeps moving. NVIDIA may dominate the most valuable chips. TSMC may control the manufacturing bottleneck. Cloud companies may own the infrastructure. Model laboratories may produce the breakthroughs. Open source communities may drive costs down. Governments may determine where the technology can travel. But the final winner may not be the company with the most impressive demonstration. It may be the organization that turns intelligence into something reliable, affordable, trusted, and useful enough to become part of everyday life. The billions being spent today are building more than models. They are building a global production system for cognition. Factories that convert electricity, silicon, data, and human knowledge into answers and actions. That system could accelerate science, reshape work, and create new industries. It could also concentrate power, strain energy networks, and lock societies into choices being made before the consequences are fully understood. The race for artificial intelligence is already changing the world. Not because a machine has crossed a final threshold, but because nations and companies are reorganizing physical infrastructure, capital, and strategy around the belief that intelligence itself is becoming an industrial resource. And when the world begins building factories for a new resource, the question is no longer whether it will matter. The question is, who will control the system that produces it?